Hello, hello. How is it going? This is the fourth and last session of our series, trying to teach you all as much as we can about IoT, about some of the interesting scenarios when it comes to connecting all kind of things. And it was like Jim really did a great job in the three previous sessions, introducing you to the world of sensors, actuators. One thing that is, I think, super important there is for everyone to realize that sensing our physical world is so much more than just temperature and humidity sensors. There's actually a lot there. And then what happens when you start connecting your sensors to the cloud? And yeah, speaking of sensors, today I want to spend the next hour, and I hope many of you will be tuning in and asking all the questions you have on your mind. We're going to talk about a different approach to sensing our surrounding world. Specifically, we're going to talk about what it takes to build an artificial nose. And we're going to talk about something that's called TinyML, essentially doing AI and doing machine learning at the edge. And we have some guests today, so it's going to be an interesting experience to see how those guests are going to let me do my presentation. But yes, building an artificial nose and some of the learning objectives for today. It's going to be like, what is TinyML anyways, right? Is this a framework? Is this a particular piece of software? Is this just a concept? What is it, and why should you care? Why should you care? You should care because it boils down to taking sensor data to the next level. Sensor data only takes you so far. I mean, it's great to be able to monitor the temperature, the humidity, whatever in a factory, in a house, in a car, but you often need more than just the raw data to take action, right? And so what happens when you start using machine learning and AI to extract more data than the raw data itself, right? And so that's essentially going to be trying to see whether the scenario is there, again, in the light of an artificial nose. And then circling back to IoT, why is it so interesting and so powerful to look at TinyML in combination with IoT and Internet of Things scenarios? The scenario I would like to go through with you today is one of an artificial nose, like I said, and it's a device that I built, and I will tell you just a bit more about why I built that device and what it does. But it's effectively a device that uses off-the-shelf hardware, that uses the WioTerminal that I hope you're all super familiar with by now, and it's able to smell things, and it can be trained actually to smell things, and that's where AI comes into play, right? So let's see how I built this device essentially, and trying to share as much as I can in terms of resources and in terms of ways to approach such a problem, so that whether you're part of the Microsoft Global Hackathon or you're just interested in learning more about WioTerminal and IoT in general, you may be able to learn from this particular application and realize that TinyML and ML on constrained devices is something that's also accessible to you and might open the door to really cool applications. So before jumping more into the meat of the presentation, a few words about myself. I'm a program manager here at Microsoft. I've been with Microsoft for a few years. I'm part of the Azure IoT product group, so working on our offerings, our cloud offerings for, cloud and more actually, offerings for all things Internet of Things. And my role more specifically is to work with communities out there, and the Seed Studio WioTerminal / open hardware community is one great example of communities that work with either open source software or software that does the job really well when it comes to IoT, right? You might have solutions out there for doing AI, ML, for doing low power wireless network. How does it work when it comes to combining those technologies and those solutions with Microsoft solutions? And yeah, my role is essentially making sure that there is a great story and great integration for people who build IoT solutions by assembling essentially hardware coming from X with machine learning solutions coming from Y and cloud offerings provided by Azure, for example, right? And so you can find me online. And today you can find me in the chat, essentially with some great support from Jenny and many other folks from Edge Impulse and from Microsoft here to answer your questions in the chat. So make sure that you use the opportunity of this presentation being live if you're watching it live. If you're not, then you may want to catch up on the recording and ask your questions in the comments. That works too. So for those who didn't realize by now, I'm French. This happens, and I like good food and I like good bread to the point where I've been trying actually to perfect my bread recipe for the past couple of decades. And one thing that I realized early in the lockdown back in the beginning of 2020 is that I was still not super happy about my bread recipe. And I wish I could use technology to let me know when my sourdough starter would be perfectly ripe, right? And so I've been tinkering, just like Jim, for many years now with all sorts of IoT sensors and Arduinos and WioTerminal, and I was pretty confident that I could use sensors and an Arduino kind of device in the form of the WioTerminal to help me figure out when my sourdough starter would be perfectly ripe. And beyond that, what I wanted to do is explore the realm of AI and machine learning, in that the kind of device that I wanted to build would ideally be some kind of device that would literally smell my sourdough starter, and I would then bake bread, and that bread would be reasonably good based on my human experience in trying to figure out when the sourdough starter is perfectly ripe. And then I would build and teach an AI model the correlation between the smell of the sourdough starter and the quality of the bread, so that over time the model would be able to, in advance, tell me, hey, you know what, your sourdough starter smells like it has reached its ideal fermentation level. You better get going and bake your bread. And so that was my idea, except that I wasn't quite sure where to get started in terms of what is AI anyways. Like many of you, I'm sure, one way or the other, you're in the same situation. You might be using AI as an end user, or even as a developer. You might be reusing some existing frameworks, some existing models, but what is an AI model anyway, and how would you go about building one, training one? If you're like me, you may have tried to go through some tutorials to teach you how to recognize images and things like that, and maybe some of the math behind it sort of eluded you. Good news is you're not alone. I'm literally telling you how I've tried and go past this sort of mental barrier, and how I ended up using my idea. Might be a silly one, right? I mean, trying to build a device to smell sourdough. It's kind of weird, but that was my excuse to learn more about TinyML. And TinyML, back to my introduction, is this a framework? Is this the name of an actual piece of software that you can download? Is this a particular commercial tool from a vendor? Is this like a Google technology, a Microsoft technology? Not really. It's more a generic term to describe this notion of doing machine learning, of teaching a computer about manipulating data and finding patterns in data, and doing it in a way where, at the end of the day, once you've once the machine has learned a particular algorithm, a particular classifying algorithm, or has learned what you wanted it to learn, then the machine where you're effectively going to run your so-called inference, the machine where you're going to do your predictions and do your AI magic, when you look at TinyML scenarios, that particular machine is really, really small. We're talking MCUs, microcontrollers, exact same kind of devices that Jim has told you all about in the past sessions. The kind of device, a WioTerminal kind of device, right? Something that has hardly a megabyte of storage, just a few hundred kilobytes of RAM, of memory, and yet that's enough to light up, to enable AI scenarios. And so that's the device that I decided I would use for my artificial nose. So the WioTerminal, I think you're fairly familiar with it. And in terms of sensors, yesterday you had a great introduction and great dive into the what is a humidity and the temperature sensor anyways. The sensor I used for smelling, I decided that it would probably be a good idea to use a gas sensor. And Seed Studio has one in their catalog. You can find, literally dozens of such sensors out there. They're not even expensive. Like you can get a gas sensor for like $10, maybe even less. This one that we're looking at here is slightly more expensive because it's effectively a 4-in-1 gas sensor. Those 4 metallic squares that you see on the PCB, on the electronic board, they are 4 sensors. One for measuring the concentration of carbon monoxide in the air, one for ethyl alcohol, one for nitrogen dioxide, and one for volatile organic compounds. And I'm no chemist, I'm no biologist, but when I started, I was fairly confident that things like carbon monoxide and volatile organic compounds, ethyl alcohol as well, by the way, would be interesting things to measure when it comes to sourdough starter, because, that's what happens when you smell, and when fermentation happens, you have alcohol, you have carbon monoxide and carbon dioxide, and it'd be great to be able to measure that, right? How does that work? I think it's an interesting, it's worth double clicking on how a gas sensor works, because again, like I mentioned, we don't always realize that we can sense way more than like a switch button, like a press button, a temperature, humidity. We can smell, we can sense and measure gas concentration. So how does the gas sensor work? Again, not being an electrochemist, I will do my 30-second intro or explanation of how it works. But essentially, you have a piece of semiconductor in the sensor, like a really, really tiny piece of semiconductor, which is being exposed to a voltage and is is powered on. And then this piece of metal, being a semiconductor, it actually reacts with chemical compounds in the air. And based on the kind of sensor, whether it is an ethyl alcohol sensor, a CO sensor, etc., it will react with different molecules and atoms in the air. And there will be a chemical reaction where some electrons will be either attracted to the metal or torn apart from the piece of metal. But those electrons moving around will effectively cause a change in resistance for the sensor, which means that this is something that can be measured in the by the microcontroller. Hence, this is something that we have access to in our software, in our embedded software. So things like volatile organic compounds, as per the data sheet of the sensor, maybe 10 parts per million of volatile organic compounds will register as 100 ohms on the sensor, whereas having way more and much more VOCs in the air, say 1,000 ppms, might mean that we have a resistance of 200 ohms, right? So that's great news, because I didn't know much about AI when I started my project, but I knew sort of that the journey would be something along the lines of, okay, I know, I mean, just like Jim, just like hopefully many of you who have started experimenting with Arduinos, VS Code, WioTerminal, like embedded sensors, you know how to acquire sensor data in your embedded software. And so the only thing that I wanted to do really was take those sensor readings and turn them into predictions. Like if my sensor reading is this, then it corresponds to this particular sourdough, to great sourdough, or it corresponds to sourdough that's not exactly ripe, and et cetera, et cetera. And so what I actually realized for the anecdote is that building a model where I would automatically have a prediction of when my sourdough starter is perfectly ripe is an idea that I abandoned quite early on, because I realized that training the model, like establishing essentially what's happening for going from the left-hand side to the right-hand side of the diagram would require me to bake dozens and dozens of baguettes, which, I mean, I didn't really want to do, or couldn't even, given how little flour was available on the shelves early in the pandemic. So effectively, I realized that maybe I wanted to train a model that would know and learn how to smell virtually anything. So it would essentially start by acquiring lots and lots of data and label the data, right? Essentially, the idea is there must be some kind of mathematical function that takes raw sensor readings and measuring how the concentration of each of the 4 gas compounds that my gas sensor can measure, how does that correlate? How does that relate to a particular smell, right? And so I would need to acquire tons of data and label the data. So essentially, the idea would be to leverage, and that's where early, like I think we're talking May of 2020, I decided that I would use the Edge Impulse tool to help me in my journey. And turns out the tool provides a great solution for essentially taking the data from my sensors, going through the WioTerminal directly to the cloud. Because at the end of the day, it's not just a handful of data points and sensor readings that I need to manipulate to potentially train an AI model. It's literally thousands and thousands of data points. And so using Edge Impulse and the Edge Impulse tooling, the idea would be that I would start by programming my WioTerminal so that it would dump sensor data to the serial console, similar to how you've seen Jim show you some kind of like Hello World examples where you would print data on the serial output of the WioTerminal. I did just that, except that the kind of data that I would output to the serial console would be the raw readings from my WioTerminal. And then by running some kind of daemon locally to my on my machine, I would route the data to the Edge Impulse cloud environment so that I can work further on the AI magic, except that it's not that magic. But yeah, it starts with data collection. So I want to show you real quick how that works, like whatever was in this diagram just before. I want to show you how it works in action and how it works live. So this is this is my desk with the WioTerminal running. Like it's actually running my my initial application. And what the WioTerminal does is, so I have the gas sensor attached to it, by the way, right? So just want to make it clear, the very same sensor you saw before on the in the slides. And so, and you see a USB cable coming out of the WioTerminal. So if I open up my my terminal here, and I could show you that straight from VS Code as well. But what I want to show you on my desktop here is what's happening on the serial console. right? And so the serial console on my desktop is effectively dumping. Like we see the raw sensor data, we see the data coming out of the WioTerminal, and right now this is the gas sensor is sort of in the air. But if I am to put the sensor in a can of coffee powder, then we're reading slightly different sensor data, right? And if we can make sure to see the my desktop as well for the live stream, that'd be great. So this is the sensor data coming out of my WioTerminal. And right now, it's going up. And if I go back to smelling ambient air, so the sensor is now back to smelling just the air, we see the sensor readings going down. So this is the raw sensor data that I need to start capturing, right? And I need to start potentially labeling this data to start thinking about potentially training an algorithm to establish correlations between the characteristics of the gas sensor data and potential smells. And so this is where I effectively stop like streaming data from my laptop and open up Edge Impulse, the Edge Impulse Studio, and we will be dumping in the chat, and I will be pointing to resources online for you to like actually know what are the pages in the Edge Impulse documentation where you can go to learn more. But I thought that a live demo might be worth 1,000 words. This is Edge Impulse, the Edge Impulse environment, with a brand new project where I want to start building an AI model that could be about doing image recognition, could be about training wake words for like having a microphone that detects wake words, or in my case, I want to start thinking about a potential AI model for smells. And so how does that work? I need to connect the Edge Impulse cloud environment, and so we are in the browser here, right? What you see on my desktop is my browser. We need to start feeding data into the system, and it's literally as simple as going back here to my terminal and using a local command line to forward data from the WioTerminal, from my embedded MCU, if you will, my microcontroller, forward the data to the cloud. And so I just need to tell my local tool, my command line tool, what is the serial port where my WioTerminal is attached to, connecting to the cloud. And now if I go back to the cloud, we should see, there we see it, that we have the ability straight from the cloud environment to trigger a data capture. And so right now the sensor is smelling ambient air. So I can be like, hey, how about we capture 5 seconds of data and we label that data ambient air, because that's what we're smelling right now. And we have great support in the online environment to also like visualize the data. Maybe I will do another data sample where I start putting my sensor in the coffee can and I start sampling 5 additional seconds of data. And let's see how it looks like. It should be fairly different. Yes, it is very different. Like ambient air was like we were reading about 500 ppms of nitrogen dioxide, and everything else being pretty low on the scale. Here for coffee, as soon as I put the sensor in the coffee can, then it starts going way up, right? And so that's interesting. That's the kind of sensor data that's going to be useful, hopefully, to identify smells, right? And so the next step is to use this raw data and get to the point where we use this data as the input to some kind of what I literally call a function. We want to identify and build a function as in a mathematical function that takes an input and which will be the sensor readings, and as an output will give us a prediction of this is coffee, this is ambient air, this is whiskey, etc., etc. So essentially, I want to get to the point where I capture tons and tons of data, right? Like here, this is data corresponding to whiskey, and then figure out how the raw sensor readings are. What is it that makes those sensor readings characterize such and such smell? And so this is where we need to figure out how, like, if I capture, say, a second or two of data, because I mean, my intuition was telling me, not necessarily being an AI person, my intuition was telling me, you know what, if I captured just a few, I mean, if I capture just a single data point for each gas, let's capture a snapshot of concentration of CO, VOC, volatile organic compounds, alcohol, and nitrogen dioxide. It doesn't tell me much, right? Because I mean, I'm reasonably confident, and I could actually see by experimenting with the sensors that both vodka and whiskey, if we're smelling booze, both would, like, as if I am to just sample one data point straight off the bottle, like on top of the bottleneck of of whiskey and vodka, both would register as 850 ppms, more or less, maybe one or two ppm. So it doesn't tell me much. It's not like I have enough information to characterize that one is whiskey, the other is vodka. So what I realized, though, is that for each element, for each item that I would expose the sensor to, the gas concentration would slightly vary over time, right? And this variation visually, especially visually through the Edge Impulse studio and cloud environment, I could see that the variations, they were different depending on the smell, right? And so if I were to capture a few seconds of data, and I quickly realized and I iterated and realized that just literally 1.5 seconds of data was plenty, I would ideally and probably capture just enough data, right? And so the next step was to figure out how this raw data would be something that I could feed into the function, the mathematical function that I was talking about earlier. And if we look at the raw data, our human brain cannot really make much of it, and a computer either, right? It's not like it's not like we have a clear vision of what's going on there. But if we start tinkering with the data, and this is something that the Edge Impulse environment guides you to do, you can start like tweaking the data and making sure that it's structured in a way where whatever information might be hidden in the data starts emerging, right? So it starts by making sure that, hey, if you acquire data corresponding to 4 different sensors, you'd better structure your data so that it's effectively looking like you have 4 different sensors and each ending in a dedicated, each ending in a dedicated bucket, kind of stuff, right? And so once you've done that, another step is, and again being guided by the Edge Impulse environment, is making sure that you normalize the data so that whatever computations you'll do later on, it's probably going to be computations in the form of trying to figure out the probability that such or such concentration of such or such gas corresponds to a particular smell. So you'd rather think about your quantities as things between 0 and 1, because at the end of the day, that's what you're looking at, right? If you have 100% alcohol, 0% carbon monoxide, and 1% nitrogen dioxide in the air, it's going to be maybe 100% whiskey, right? So that's another thing that is that you need to do in your sort of thought process. But something that the tool guides you really well to do. And once you've done that, and this is where things clicked in my brain, and I will do my best to make it click for you as well. You may have heard about feature extraction. When it comes to machine learning, one thing that you want to do before even thinking about building an AI model is doing feature extraction. And that's exactly what we're looking at. Like here, this array of data, the numbers you see here are way more meaningful than what we had right here. Here, this is raw sensor data. Here, this is the extracted features, and this is the things that really characterize the smell. And that's something that I eventually ended up calling the olfactory fingerprint of the different smells, because what you're looking at here is fairly simple math, very simple statistical functions that we ran against the raw data to extract for those like 1.5 second time slices, time windows. We extract the average, the minimum, the maximum, the standard deviation, things like that for the gas concentration, so that we have numbers, like single numbers that characterize on average how the smell, how strong such or such smell is alcohol-wise, but also how much it varies, right? If the standard deviation is really close to zero, then it means that the smell is fairly steady, right? If the standard deviation is slightly higher, then it means the smell is maybe more volatile, right? And so that way we capture interesting information, right? Or at least we capture information that at the end of the day, I realized was enough to effectively train a model. So if we go back to what we were trying to accomplish, the idea was trying to go from raw sensor data to a prediction. And that's exactly what we do. And I will show you real quick in examples what would be essentially the next step to do this kind of feature extraction and eventually train the model. And you see that it's reasonably straightforward, but it really starts with feature extraction. And that's what was missing in my brain when I started building the AI nose, and something that hopefully is more tangible for you now as well. This idea of, okay, I have raw sensor data, I need to turn it into interesting features. And in simple terms, like the average, the minimum, the maximum, and the standard deviation, in simple terms, it's really things like the intensity of the smell, the volatility of the smell, things like that. Those are the things that I extract through the signal processing block. And then comes the time to feed those, feed the olfactory fingerprint in a neural network. And to me, a neural network, when I would read some literature around it, I would have things like fully connected networks and activation functions and those kind of terms thrown in my face. That was kind of too much for some reason. I realized that it's actually way simpler. It doesn't need to be necessarily complex when it comes to building your first AI model, at least. And so in my case, what happens, the kind of function that I needed to build, or the kind of equation I needed to solve, was literally finding a function that as an input takes the what I did call the olfactory fingerprint of the smells. So the 20 things and the 20 inputs that you see here, the 20 inputs to the neural network are effectively for each of the 4 gas sensors I have. Those are the 5 characteristics that I extracted. So you would have the average, the minimum, the maximum, etc. for so that would be for CO2, for CO, and then you would have the average, the minimum, the maximum, etc. for the other sensor, and then the third sensor, and then the fifth. And I think I probably put 6 in one of the buckets, but yeah, I think you get the idea. I want to build a function. I want a model. You call it however you want. Something that takes as an input the characteristics of the smell, and as an output tells me what is the likelihood that the smell is A, B, or C. So in my case, I initially trained the model with ambient air, whiskey, and coffee. So I want a function that takes as an input the concentration of each gas, at the average, minimum, maximum, etc. And as an output tells me, oh, this is 98% whiskey, 2% coffee, and 0% chance that this is ambient air. And effectively training the model, what people refer to as training the model, is trying to solve the equation by doing a lot of trial and error, essentially, although the learning algorithm can be slightly smarter, but trying to figure out what is to solve the equation by being exposed to the so-called training data, essentially telling the model, hey, this particular input, this is something that we know for sure is 100% whiskey. So try and solve the equation assuming that this input gives as an output 100% whiskey, 0% ambient air, 0% coffee. And then do that over and over again by having training data and trying to find what is the best model for the training data. If we go back quickly to Edge Impulse, granted that I start acquiring enough data, and in my experience, having just a few minutes of data for each smell was enough. As soon as you have enough training data, you can start trying to design the model, right? And designing the model can be reasonably simple. You have lots of support in their environment. And essentially, as an input, it's going to be the raw sensor data. In my case, it's gas sensor data that I acquire at 10 hertz. So every 100 milliseconds, I would read sensor data. I want to find a way to route this data through my signal processing algorithms, my neural network, so that at the end of the day, it gives me a prediction, right? So when it comes to extracting the meaningful features, I just need essentially to get, let me be guided by the Edge Impulse wizards. And I have some interesting explanations here. And one is, you may want to use a flattened processing block if your data comes more or less in the form of slow-moving averages, like temperature data and things like that. So I feel like that's the kind of data that I'm going to manipulate, right? At least I'm not manipulating images or audio. So using a flattening building block is probably going to be interesting. And then once I have flattened my data and extracted the key characteristics, and essentially once I have gotten rid of the notion of time, at the end of the day, I don't really care whether I smell during 1 second, 2 seconds, 3 seconds. What really characterizes the data is average concentration, the standard deviation, things like that. So that's why it's called flattening in a way. And then once I have extracted those characteristics, then I need to run the data through a classification algorithm. I want to learn patterns from the data so that whenever I present my algorithm, my model with new data, it's going to be able to make predictions, essentially. So that's the kind of workflow that you want to go through if you're interested in playing with TinyML. Maybe for you, it'll be with gas sensors as well. Maybe it'll be with temperature sensors, with humidity sensors, with torque sensors, weight sensors. Could be anything really, right? But you get the idea. You start capturing sensor data, feeding the data into the Edge Impulse environment by routing the data directly from your WioTerminal to the cloud through your desktop computer, you acquire the data, and then you start designing your model. And if I wanted to go one step further, I could just save my impulse and show you slightly more, and some of the things that I've shown you in the slides, how would they look like in the Edge Impulse Studio. I have raw data corresponding to the evolution of the concentration of CO, alcohol, etc. for coffee, for ambient air. So really quickly, I can try and turn those into extracted features. And what I described before, right? Like scaling the data so that we have numbers that are going to be between 0 and 1 as opposed to what they are right now, extracting the average, the minimum, the maximum, RMS, standard deviation. Those I'm going to assume that I don't necessarily need them. And let's see, I can generate, like actually extract the features that correspond to my training data set. And then we're going to have some really nice visualizations to visualize in on a 3D graph and with a 3D axis how well ambient air and coffee are, how different they are when it comes to the average concentration of each gas, the minimum concentration of each gas, and essentially see if the features that we've extracted are really characterize the smells. It looks like they might, at least like the ambient air is completely like in a different space than coffee when it comes to the concentration of nitrogen dioxide, carbon monoxide, and ethyl alcohol. So that's interesting visual feedback. And so the next step would likely be to build the actual neural network, build the figure out what should be the parameters to the equation we're trying to solve. That one equation that takes as an input the characteristics of the smells and as an output would give me the predicted smells, right? And so we could actually try and train the model, but we have so little training data that it probably won't make a lot of sense to train the data. But I mean, I can show you at least the way the workflow there, and at the end of the day, we would have a model that is effectively the kind of model that we would be able to deploy as a library, as an Arduino library. Just like Jim yesterday gave you an introduction to the kind of libraries that you may use for connecting to Azure IoT and to Azure IoT Hub. Here, straight from the Edge Impulse Studio, I can build an Arduino library that I can download on my machine and then start using in VS Code or in the Arduino IDE that I can start and use to build my embedded application and to add TinyML to my embedded application. So that's pretty interesting. And yeah, I mean, again, there's tons of literature out there for you to learn more. But essentially, the next step, once you've trained a model, is to start using it in your code, right? As opposed to having your embedded application kind of naively manipulating your raw sensor data and displaying the raw sensor data on the serial console or on the LCD display of your WioTerminal. You can start taking this raw data and feed it into the Arduino library, into the embedded library that you get out of the Edge Impulse IDE. And that particular library, what it will give you as an output is exactly what it's been trained on, which is taking raw data, processing the data to extract the features, etc. And it's going to be super transparent for you and give you a prediction of what smell it might your sensor data might correspond to, right? And now that we have trained the model, we can see that the model is actually not able for some reason to smell coffee. We probably don't have enough data there, but we have a model, and we would be able, straight from the Edge Impulse IDE, to build an Arduino library. And like I can show you real quick, right? But it's letting me download a library that I can then unzip on my machine and start manipulating in Visual Studio Code. So that's pretty interesting. And we have essentially, by doing that, we can start turning our raw signal coming from our sensors into something much more meaningful, right? Raw sensor data only takes you so far, like I think I said before. But if you start being able to turn the raw sensor data into insights, like, hey, this smells like coffee, this smells like whiskey, then you open the door to way more interesting use cases, which I actually want to talk about, like in the remainder of the presentation. I want to tell you what happens when you start combining TinyML and potentially things that you do through Edge Impulse with IoT. The nose, as you saw it in the introduction, is effectively a funny-looking kind of device with a 3D printed nose enclosure and so on. But the main feedback to the end user is through an LCD display, which is, that's great, which means that locally you can tinker and play with the nose, but it very much feels like a toy to some extent. You can like maybe impress your friends by being like, hey, see, I have an electronic gadget that can smell whiskey, coffee, etc. But then it doesn't really feel like we have some interesting commercial or industrial scenarios by doing just that. I mean, yes, maybe the nose can beep or emit some kind of sound when it smells a dangerous gas, and you can give some feedback to the user that they might want to open the window to get some clean air. So that's there's a question, I think, from someone on whether the raw data that we get from the device, can it be pushed to other things? Yes, it can, and that's actually where IoT comes into play. And that's why actually you see on the device this wireless wireless communication icon here. I ended up connecting the device to the internet, to the cloud, to Internet of Things platforms, because I realized that there's tons of really interesting use cases when it comes to an artificial nose and a smart artificial nose for things like you want to optimize the way you send people, like if you're in the business of cleaning restrooms and office buildings, etc., you send your staff to clean the rooms, probably with some kind of regular schedule, right? Every day at 5 a.m., it's someone's duty to go and clean a particular building. But what if you could deploy a device, ideally like in a remote location, and ideally the device is not even visible to the end user, right? The device can smell how clean the air is, and automatically the device reports the data to some kind of internet backend, so that whenever the device smells that something, that the air is a bit stale, then you can get a notification, right? And so that's exactly what IoT is about, right? And so you've seen yesterday and in the previous sessions that, of course, one good use case for IoT is to use raw sensor data, like to turn the sensor data into some kind of telemetry and some kind of signal that you send to the internet backend. But what if the signal could be sort of a signal on steroids in the form of a prediction, coming out of a TinyML, like out of a machine learning algorithm? And that's exactly what I ended up doing and building, and effectively looking at what some would call AIoT scenarios, AI plus Internet of Things. And so effectively, the nose can be connected to the internet so that you can have the nose on one hand, the cloud backend on the other, and then you can start thinking about, and to the question earlier about can the telemetry be sent to other things? Yes, it can. And so the telemetry coming from the nose can be fed into a cloud environment so that all the history of like how the gas concentration evolves over time in a particular room, in a particular building, in a car, I mean, you name it, you can capture this data in a cloud environment and in a cloud database maybe, so that you have access to all that data later on to process it, to do some post-mortem analysis of what happened in your environment, to use the data maybe to also refine and improve the quality of your AI model. And yeah, that's definitely something that you can do. And it can go both ways. And that's also very interesting. If you think about AI for smells, initially, maybe you build a model that can tell clean air from stale air and make the difference between fresh air and air that means that maybe you need to do some cleaning in the room. That's at day one, but maybe a few months down the road, you figure out that the sensors you've used in your hardware design would be good enough to identify, to pick up the smell of COVID. And literature and research actually seems to imply that it's effectively possible. And so what if, without any human intervention whatsoever, you could use the cloud to deploy new updates to your AI model, right? And so that's definitely something that would be possible. And so in my case, what I ended up doing is connecting the nose to Azure IoT Central, right? And going from a connected, from an artificial nose to a connected artificial nose. And here, I'm essentially just connecting the dots between what Jim told you about in the previous sessions, which if you missed, you can definitely find the on-demand versions on YouTube or on MS Learn. Please check them out. But essentially the idea is you take your device and your embedded code and whatever is meaningful in your embedded code, your raw sensor outputs, the outputs from your machine learning algorithms, and you feed those into the Azure IoT SDK so that eventually they make it to the cloud. One thing that's actually interesting, and I won't dive too deep into that, but it's actually interesting to think about modeling how your IoT gadget, how your IoT device's data looks like, so that you can address the potential issue that might bite you quick enough, which is sending data from an embedded device like the WioTerminal to the cloud is really easy. And Jim showed us that yesterday. Literally one line of code, you can send telemetry to Azure IoT or to AWS IoT or to any other MQTT broker. It doesn't really matter. It's pretty easy to send data. But if the data really is just, say, a number that says 73, what does that mean anyways? Like, is when the nose is sending 73 to a cloud backend, does it mean that it's 73% of humidity? Is this 73% of battery left? Is this 73 ppms of nitrogen dioxide concentration in the air? It depends, right? And so one thing that is important to do is to model the data, and it's something that in the Azure IoT land we do using something called DTDL, the Digital Twin Definition Language, and I encourage you to do some readings about it, or more likely, I think what would be easier is for you to look at the code of the artificial nose and to see how, in practice, the artificial nose is leveraging DTDL so that when the nose connects to the Azure IoT platform, the nose is effectively a so-called plug-and-play device. So as soon as you configure the Wi-Fi credentials in the nose's WioTerminal, like Jim demonstrated in his videos and tutorials, then as soon as you have Wi-Fi connection, you are effectively have data flowing into the Azure IoT backend, and not only data, but data that is meaningful, data that starts showing up on your IoT dashboards as effectively being VOC concentration, NO2 concentrations, and things like that. So that's it's pretty important to not necessarily at day one to think about describing the contract of your devices for your devices data and thinking in terms of plug and play and so on. But it's good to introduce that in the solution so that you build a solution that's effectively more interoperable than if you were to not use something like DTDL. But yeah, at the end of the day, using TinyML/Edge Impulse plus Azure IoT, you build a device that is effectively a reasonably constrained device, a device that can be powered out of battery. And that's a device that not only manipulates sensor data, but that also makes sense out of the sensor data, right? And starts doing inference and predictions on the sensor data. And over time, you potentially improve your model. And also, something that's really interesting, and that that's where Jim more or less left us yesterday in the presentation. IoT, like connecting the WioTerminal to some kind of IoT platform, whether it is to send raw sensor data to the platform or to send the results of your TinyML inference, it's only the beginning, right? You route the signal to the cloud, and then you start making fun and having fun and making business with the data. Things like, oh yeah, I've just picked up the smell of foul air in a particular building. What is the rule that I need to trigger in my ERP, in my business application? I need to send an SMS to John, because it's John who was supposed to be cleaning this room today. Oh wait, my Outlook system, my LDAP is telling me that John has called in sick today. So the rule will be dynamically adapted so that we take another action, right? And it's definitely something that you want to do in the cloud, because there's no way the WioTerminal, the local device, the tiny MCU, will have access to something like the schedule of all your employees, right? So you want to complement your edge environment, your MCUs, with all the power and all the dynamicity that the cloud can bring, right? And so connecting the IoT device to the cloud really is like literally just the first step. And you want to use the cloud to visualize data in real time, to contextualize the data with your enterprise systems, and so on and so forth. And like feeding the data, like entering through the Azure IoT pipeline means that you all of a sudden have access to the entire Azure/Microsoft Galaxy for sure, right? So that's that's one thing that I wanted to make clear. Skipping quickly on that slide because I want to make sure that I can wrap things up before calling it a day. In a nutshell, like TinyML, to me, it's really important in that it allows you to make your devices smarter, and it doesn't require necessarily tons of processing power. Even a tiny device like a WioTerminal can run AI and machine learning, but when you start combining that with the cloud, then you can leverage like both the strength of having a tiny device, but also all the power of the cloud. And the artificial nose, everything is accessible online. The code it's on a GitHub repository. You can even order a developer kit that comes with the WioTerminal plus the dedicated sensors that you might require. And with that, I would like to thank you all for your attention. I think I'm running out of time, so some of the questions that came in late, either some of my colleagues will already have had a chance to answer them, or I will spend the next few minutes in the chat answering them. But yeah, thanks all. I hope you will get started hacking with the WioTerminal, with temperature, humidity sensors, gas sensors, or any other sensors really, and start connecting your solutions to IoT platforms. Thank you.